Hello, I am Konstantina, and today I will talk to you about Bayesian modeling with applications on relational data. I'm currently a postdoc in the University of Oxford, and I'm really glad that I'm presenting this talk to you today. And also, please feel free to ask any questions that you might have on the side chat box. Today we'll speak about, first of all, modeling, what modeling is. I will start the talk with explaining a bit abstract how we define a model. Then I will make the talk more specific about Bayesian modeling and especially nonparametric modeling. And I will try to be quite clear about the definitions of every term. And then I will give an example of Bayesian nonparametric modeling in relational data and more specifically in genomics. So the first question is, why do we even care about modeling? The short answer is that we have so many data nowadays that the only way to explain this data is actually through statistical modeling, through actually representing the data through models. The data come from different sources, from society, for example, we have the social networks, Facebook, Twitter, Instagram, so on and so forth. Then they also come from the scientific domain. We have data that come from scientific experiments, from biomedical data, or even climate data from different institutes. And finally, we have the business domain that has more time series data from electronic trading, for example, or e-commerce, or even advertising. So it's urgent need that we actually build models to explain and visualize this kind of data, because only then we will be able to leverage the information and make predictions and actually make useful actions upon this kind of information. If now we are asked to define what a statistical model is, then we need to find a mathematical way to define it. Under that notion, a model actually is a definition of the data generating mechanism using mathematical terms. In more simple words, when I define a model, I use mathematics, the science of maths, to explain how the data is generated. So imagine, for example, the following setting. We observe what we see here on the left side of the slide is an axis X where I have put some data points, and assume that we observe this kind of data points which I now define indicate by Y. So given this kind of data now, the question that arises is how was this data generated? And what I'm actually asking is, what is the model, the data generating mechanism that gave rise to these observations? And also another question that we might ask is, if now we assume an unseen point Y, what can I say about that? What's the prediction that I can make? The first step towards answering these questions is that we need to make some assumptions. And the assumptions that we are making are actually the ones that build the model. The assumptions that we make are a quantity in a model using the parameters theta, are actually the parameters of the model. In the specific example, given these parameters, then I sample the data points from a probability distribution. And the probability distribution is the data generating mechanism, and is actually defined and dependent on the parameters theta. So the takeaway message is that the statistical model is actually a data generating mechanism that depends on parameters. By choosing now different kind of parameters, I choose a different model. In the specific example now, I make the assumption, as you can see now in the plot, I make the assumption that the data generating mechanism is a Gaussian distribution. And the parameters that I assume for my model is the mean and the sigma and the standard deviation of the distribution. So choosing a data generating mechanism is equivalent to choosing the appropriate model. And the parameters is a basic characteristic of the model. Another example now, imagine that I have that I observe this data as I see on the left side of my slide. These are data, two-dimensional X and Y data. And now the question that I ask is, what can we say about the unseen Y at an unseen input X? So I need to make a prediction. But before that, in order to be able to make the prediction, I need to define my model. So I make an assumption. The assumption that I make here is, okay, I look at the plot, I say, this looks like a linear regression. Maybe if I fit a line, then this will do the job. This will be good enough. So I fit a line on the plot. And the line has some parameters, theta, which you may know them as coefficients or weights, if you like, in the more deep learning and terminology. So I fit the line, and that's how I explain the data. I use a line, and I say that the data are actually produced from a linear regression model. What I didn't discuss so far is about the uncertainty, and the uncertainty is intrinsic in every data that we see. In other words, uncertainty actually says that we're never sure about what we see, and also we're never sure about the assumptions that we make. So we need to introduce this uncertainty to encode this uncertainty into the model. And this uncertainty comes in many forms. For example, we have uncertainty when we measure the data, the Y's that we observe. We have uncertainty about the values of the parameters. In the previous example, the parameters were the coefficients of the linear regression. But we also have uncertainty about the model that we chose itself. Are we sure that this is a linear regression model? Maybe it's a logistic regression model. How can we be sure? So we need to introduce this uncertainty, because only then my model is more flexible. The way to do that in the Bayesian framework is by actually following the Bayesian principle. And it is very simple. The idea is that all forms of uncertainty should be expressed using probability distributions. For example, going back to the previous linear regression model, I introduce uncertainty because of the measurements of the observations by adding epsilon into the model. The epsilon here is the noise. And this noise is sampled from a Gaussian distribution. By doing so, what I do is that I define a probability distribution over the observations, which is a Gaussian distribution with mean given by the linear model. I also account for the uncertainty onto the parameters by defining a probability distribution over the theta. And finally, I define a probability distribution over the model itself to account for the uncertainty whether the model is adequate enough to explain the data or not. In short, what I did in the Bayesian principle way is that we assumed distributions over every unknown parameter. And this is exactly the probabilistic modeling, or else way, this is the Bayesian probabilistic modeling. If we want to elaborate more on this, the Bayesian modeling can also be described by using graphs. And the graphs indicate the relationship between the parameters. In our example here on the left side, I observe the x and the y's of the linear model. And then I don't know anything about the theta, the weights, and about the sigma, the standard deviation of the nodes. That's why the x and y are filled with gray color, while the theta and the sigma are not. In this model, in the Bayesian modeling, I also define the likelihood, which you may be aware that is the probability of the data under the specific model that I chose and the specific parameters theta. And since the data y's represented here in the set D are independent and identically distributed, I can take the product to define the likelihood of the probability of each data point. I also define the prior over the parameters because that's the way to introduce my uncertainty about the possible values of theta. So I call it a prior because this is my prior belief before seeing the data, how theta might be, what the values that theta might take. The question now that arises is, I need to learn theta, the actual value of theta. I need to learn that parameter. The way to do that is by using the very well known in the field that is called Bayes rule. Let's see what this Bayes rule does. What this Bayes rule does is actually computing the posterior. This is the posterior distribution over the unknown parameters. Remember, I defined a prior over the parameters theta, which is actually my prior belief over the parameters. Now, I define the posterior as indicated by the Bayesian rule. And this posterior is proportional to the likelihood times the prior. This is a very important note. The posterior is proportional to the likelihood in the prior. This means that my prior belief over the parameters is being updated after I have seen the likelihood, after I have seen the data. Let's see, let's become more explicit about what we mean by that. Let's see here on the left side, I have plotted with blue my prior belief, which is a Gaussian. I have plotted with pink the likelihood, the distribution of the data for the parameter, and then I have plotted with green the posterior. As you can see here, I have two driving forces about my updated belief, the blue one from the prior and the pink one from the likelihood. And the posterior, which is the green, it's exactly in the middle. That means that in a way, it compromises from the two different driving forces. So I update my belief by using information from two sides, from the prior and from the likelihood. And this is exactly what the Bayesian learning is, what the Bayesian inference is. I don't compute one specific value, but I compute an updated belief. By having done so, I'm now also able to make predictions using marginalization. That means, for example, for an unseen data point y, I compute the probability by marginalizing over all the possible values of theta, as you can see here. So by doing so, what I achieve is that my prediction is actually a weighted average over all the possible values of theta. I don't care about a specific point estimate of theta, but I consider a distribution over theta, and by doing so, I consider infinitely many values of theta. And I take the weighted average by using these infinite values for the prediction I want to make. If you think about it, this is the intuitively correct way to do so, because I have an updated belief over theta, so I want, and this is distribution, so I want all the information coming from this distribution to be introduced into my prediction. Not only by only information from a point estimate, but from the whole possible values. Question now, why is this even useful? Why don't we just take a point estimate? First of all, uncertainty is taken into account, and taking uncertainty into account is intuitively right. Don't you agree? We're never sure about the prediction we want to make, or we're never sure about possible values. So what we do is that we say like 50% that, 30% that value, 20% that value. So it's good if we incorporate the human way of thinking into our statistical modeling as well. What I have plotted here is that the point estimate, as opposed to the posterior distribution given by the Bayes rule. I don't have a point estimate anymore. I have the posterior as I plot again, which is actually a compromise between my prior belief and the evidence, and it's intuitively right. I'm also able to naturally handle missing data. There's, for example, if I go to the previous linear regression example, I show now that here in my plot that X is also unobserved. If using the Bayesian principle, I go and I assume a probability distribution over X, P of X, Then I can sample from it, and I can fill in any missing data. And then the Bayesian, and then the Bayesian computation, by following the Bayesian computation, I can compute the posterior, and I can sample the unknown value from the updated posterior. Let's move on. But before moving on, let's recap what we have seen. So in order to build a model, what do? We write down our assumptions in order to build our assumptions that actually define our model. And these assumptions are assumptions about the parameters, the distribution of the parameters, about the noise that we need to introduce, and so on and so forth. And then, given the data that we observe, you use probability theory, and actually you use the Bayesian theorem to update our beliefs and also to make predictions about the model. The problem now that I haven't mentioned so far is about the number of parameters that I define. All the models that I described so far are actually parametric. That means that we assume a finite set of parameters. I can count them, they're finite. By doing so, the parameters are enough to actually explain the data, as we said earlier. That means that the parameters capture everything that there is to know about the data. Knowing the parameters, then we don't really want to know about the previous data in order to sample from the mechanism. However, by defining a finite set of parameters, we actually introduce some constraints into the model. We say that the model is as flexible as the number of parameters can allow. So the complexity of the model, in other words, is bounded. But this is not always what we want. And this might actually affect the efficiency of the model. Are we sure by choosing the specific parameters and the specific number of parameters, are we sure that the model that we construct is good enough in the sense that capture the reality of the data? Are we sure that the model is chosen correctly? Maybe we need more parameters or we need a different prior. We're never sure about that. In order to make it clearer, consider the following example. Consider that we have some data as the ones I plot here. These are my observations. And these observations can be assigned to clusters. In a better example, consider these observations to actually indicate the preferences of people over movies. In one cluster might be people that prefer horror movies, in another cluster people that prefer romantic movies, in another cluster science fiction, horror, drama, so on and so forth. This is a real complicated, this example is a real, is an example of data complicated. So, and if I'm asked to define the model, I need to define the number of clusters that I will assume for this model. And I need to define also a prior over the number of clusters theta in order to be able to answer how many clusters do I see here. The problem arises that if you put constraint on the number of clusters, then the model might not be well defined. That's because there are so many different clusters that the number reaches to infinity, and it's impossible to capture them with a finite set of parameters, with a finite set of clusters. Consider, for example, all the possible combinations of different categories of movies categories. Horror movies, drama movies, love, romantic movies, science fiction movies, movies with Jack Nicholson in horror movies, movies with Jack Nicholson in romantic movies, infinitely countable number of clusters. So using a parametric model will only capture some of the data and not all of it. So it won't be good enough. And in other words, using a finite number of clusters is quite reasonable. So the question is, how do we adequately capture our beliefs, our prior beliefs about the number of clusters? The answer is by using nonparametric Bayesian models. Let's see what is a nonparametric Bayesian model. A short definition is a model that actually assumes an infinite dimensional parameter, theta. Infinite number of parameters. Infinite dimensional in the sense that it is finite but unbounded. What I mean by that is that in a specific data set, we assume an infinite number of parameters, but in a specific data set, only a finite subset of them is represented. However, it's possible to assume an infinite number of parameters. Then we have the data that speaks itself. That means that the model is able to find the number of parameters by looking at the data. I don't have to predefine the number of parameters, but the model chooses the numbers of parameters by looking at the data. So for a given sample size, invokes the model, the Bayesian nonparametric model, which now I might call BNP, invokes only a finite subset of them. And the complexity of the model can grow as the data size grows. The more data I show, the model chooses more parameters. It's more in a sequential way. So it's more flexible as opposed to the parametric case. The question now is, I talked about infinity. How am I dealing with infinity? The Bayesian parametric model puts a prior of infinite dimensional model by actually using the so-called stochastic processes. The examples of stochastic processes used widely in the BNP domain is the Dirichlet process, the Pita process, the Gamma process, the Chinese restaurant process, the Indian buffet process, so on and so forth. What I will talk about now is the Dirichlet process, and going back, I'll talk about the Dirichlet process and the Pita process, and also about the Chinese and the Indian buffet process. Let's start with the Dirichlet process. But before that, I wanna see whether people have any questions. Yes, Chinese Indian process. I will explain what this is. These are funny names, but people most of the time come up with funny names. Yeah. Yes, Stephen. Chinese and Indian buffet process. All right. Let's start with the Dirichlet process and the cluster allocation. Assume now that we have the task of assigning people to clusters, for example, based on their movie preferences, as we discussed before. So we need to build the model. The parameters now that we assume is the parameter theta, which is the probability, with a vector of probabilities that says how probable it is that I'm assigned to a specific cluster. And then, given this parameter theta, I sample the cluster assignments from the data generating mechanism. So what is the Dirichlet process now? The Dirichlet process is actually a distribution over distributions. But I don't want you to get confused, so think of the Dirichlet process as a sample G, which is actually an infinite vector of probabilities. So G here can be thought as a set of points, k, with k goes to infinity, infinite number of points, and each point is associated with a weight omega, which is actually a probability between 0 and 1, and a location, which we don't really care for the time. Think of J, I repeat, as a vector of probabilities, W's, an infinite vector of probabilities, can be an infinite size, infinite number of omegas, and its omega is between 0 and 1. And the sum of this of the probabilities should be equal to 1. What I have plotted down here is 3 different samples from the Dirichlet process. As you can see in every sample here, the first, the second, and the third, is Dirichlet process G is actually a set of points, a set of sticks. They have a location here on the axis, and they also have a height, and their height here, the height of each stick, the height of each point, is actually a probability. Why is this useful? This is useful because by considering this infinite vector of probability sum from the Dirichlet process, I can actually assign objects to clusters. I can have a partition. How is this done? So after having sampled the infinite vector from the Dirichlet process, forget about the confusing sum. Think G as an infinite vector of probabilities. Then, given the infinite vector of probabilities, I assign its object out of n objects into a cluster by looking at the cluster probabilities given by G. The result that I take after this procedure is clusters that have objects in them. They are non-overlapping, so each object is assigned to one cluster and only. And I call the corresponding distribution over the partitions, over the clusters, which now assume that the cluster is K, as the Chinese restaurant process. Okay, the Chinese restaurant process is actually the Dirichlet process repeated in the way that I described, but defines the distribution over partitions. And this number of clusters can be infinite. And by looking at the dataset and by using some inference mechanism, the Chinese restaurant process is able to learn the number of K, the number of clusters that are represented in the dataset. So, takeaway message before moving on is that the Dirichlet process and actually the Chinese restaurant process defines a non-overlapping cluster partition with the number of clusters possible to go to infinity. Now I move on to the beta process and the feature allocation related to that. The beta process is also a non-parametric process. As a motivating example, think that we have people and we want to assign them to classes based on their hobbies. The difference now is that while people before I was assigning them to movies, to clusters which were non-overlapping, here assigning people to hobbies can result to overlapping assignment. So that in other words, people can belong to more than one class at the same time, because people can have more than one hobby. For example, I like yoga and I go climbing at the same time. So these are two classes that I belong to. So the first step to define my model is actually to define a distribution theta over the classes, which I sample from a distribution. So theta here should be the probability of me being assigned to the classes, to each of the class. And then, by giving this probability theta sample from a probability distribution P, I decide about my assignment by sample from the data generating mechanism. Let's make it clearer. So, let's talk about the beta process in maths. A beta process is again a sample from a stochastic process. It's actually a stochastic process, sorry. So, B sample from a beta process is again an infinite vector of probabilities. The difference now here is that P, which is the probability between 0 and 1, doesn't necessarily add to 1. Apologize, here this omega should be P, not omega. I repeat, P, a sample from a beta process, can be thought as an infinite vector of probabilities which do not necessarily sum to 1 now anymore. They're independent, they don't necessarily sum to 1. By assuming so, I allow, as I will see later, for an overlapping assignment to classes. Each data point now that is assigned with a probability P actually refers to a class, to a category. How do I now construct the class allocation? It's a two-step procedure. First, I sample from the beta process, which now I repeat again, is an infinite vector of probabilities. And then, after I have sampled the infinite vector of probabilities, I sample from a Bernoulli process. Don't get confused. This is a very simple thing. What is happening is that after I have sampled the infinite vector of probabilities, for each n, for each person, for each object n, I flip an infinite number of coins, and each coin is given by the probability P. The number of coins is K as the number of classes, and each class is associated with a probability P. And then for each class, I flip a coin, and the coin will give me result 0 or 1. 1 if I belong to that class, 0 if I don't. So the result of this process is a binary vector of allocations. Let's use some cartoon matrix here. What I see here, what I plotted here, what I depict here is a binary matrix. I have an infinite number of k of classes, which are the number of columns here, the vertical, and I have a number of objects here, which are the rows. I think there are 8 here. Yes. Then each column, which is a class, is associated with a probability p, which is sampled from the beta process. Then I fill in with 0 and 1s in the second step, where for each class, for each column, I flip a coin to decide whether this object will be assigned to that class or not. And that's how I construct the future allocation matrix. The matrix that indicates whether I will be assigned to a class or not. The corresponding distribution over the allocations is called Indian Buffet process. In other words, a sample from the Indian Buffet process is a feature allocation matrix. I repeat, in short, by following this two-step procedure, sampling from the beta process and then sampling from and flipping coins in the Bernoulli way, I construct a sample from the Indian Buffet process. The difference with the Chinese restaurant process is that here I allow for a multi-membership. I don't know if there is, how do you define the non-overlapping clusters? Sorry, I just saw Dr. button. Non-overlapping clusters means that I'm only able to assign each person or each object to one cluster. So each object cannot be assigned to more than one cluster at the same time. This isn't the Chinese restaurant process. Well, in the Indian Buffet process, I'm allowed to assign the objects to more than one class or cluster you like at the same time. It depends on what kind of models you want to construct. I hope this answers your question. Let's now present a model that actually implements both of these processes, uses both of these nonparametric processes, and it's actually a model that we implemented. As a motivating example, assume now that we have a friendship network, that means that we observe some links between people, some like friendships between people. And we actually assume that the way these links are constructed is because people are associated with some classes, and for example, they belong to the same college, they go to the same department, or they belong to the same sport team. But also for each class, we assume that there are clusters that they belong to. For example, in a college, they might go to the Pembroke College, to St. John College, or for the department, they belong to the engineering department, to the department of chemistry, or to the department of natural sciences. And for the hobby, the sport team, we might have football, tennis, etc., and so on and so forth. So it's really important to understand that here I have classes and I have clusters. Classes are the upper level of hierarchy, while cluster is the lower level of hierarchy. The classes are the college, the department, the sport team, while the clusters are like the more grained way of representing its class. The Pembroke, the St. John's for the college, or for the department, the engineering and the MAMS, and for the sport team, the football, the tennis, the volleyball, and so on and so forth. So how am I implementing this, modeling this kind of hierarchy? Probably you might be able to relate to what we presented before by considering the Indian Buffet process to assign the objects, the people to the overlapping classes. And then for the members of each class, I use the Chinese restaurant process to assign them to non-overlapping clusters. If I want to, if you like, please have a look here on the left side where I have like used some matrix, class assignment matrix. I have here the rows, which are the people, the objects, and then I have the columns, which are the features. Please think of the feature as the classes, the overlapping classes. For each object now, I use colors to indicate that the first object is assigned to the first class, to the third class, and to the fourth class. The second object is assigned to the first, to the second, and to the third class. So on and so forth for all the objects. Now, I look at each column, which is equal to looking at each class, and I see how many people or objects are assigned to that class. For example, in the second column, we have 1, 2, 3, 4, 5 people assigned to the same class. I use different colors to indicate different kinds of clusters, non-overlapping clusters. For example, looking at the second class, I have the second and the fourth object and the last object belonging to the red cluster, while the fifth and the sixth object, they belong to the blue cluster. I have classes and I have clusters. Classes allow for overlap for multi-membership and are the columns, while clusters are found inside the classes and they are non-overlapping. How I define them? Using the Indian Buffet process, where I sample from the Indian Buffet process, I sample the allocation matrix and then the Chinese restaurant process to define the cluster membership. To be more mathematically correct, I here present the model. I present the model fully. What I see here, maybe I need to move on as I see I'm running out of time. I can be really brief here. So these are the two steps where I first sample the feature allocation matrix Z from the Indian Buffet process. Then I sample for its M, where M is the class, I sample the cluster allocation from the Chinese restaurant process. And then I define a weight matrix sample from a Gaussian distribution, and the weight matrix is defined for its class and actually indicates how probable there is to be a connection between members of different clusters K and K prime found in that class. The interesting part is how I design about the link, and the way I decide about the link is actually using a Bernoulli distribution between I and J. I and J are two objects, and I give as an input a sigmoid function that actually says that only the common features that are simultaneously on affect the link probability. In very simple words, the way I decide for a link probability between two objects is by saying I care only about objects that belong. I only look at the categories that these two objects are members on at the same time. And then I look at their cluster assignments to decide how probable there is to be a link between them. It's very intuitively right. So let's now go and see like 3 more minutes now, and I think I'll be done. Bear with me if that's all right. Let's see some applications of this model in genes. So I have 2 applications of gene interaction networks. The first is a very small data set of 156 genes. The observations I have here are plotted here on the true links. So the white indicates that there is an interaction between these 2 pairs of genes. So this is a square matrix of interactions. The white means that these 2 genes, of course, this is symmetric. These 2 genes are actually interact. That means that somehow they're involved in the same process. I compare the model, this hierarchy model, by models that assume flat clustering. The first one is the infinite relational model that assumes only clusters, non-overlapping clusters, while the second one is the latent feature relational model, which actually assumes only classes, multi-membership classes. And what we found is that our model, the infinite relational model here on the last column of the table, does significantly better in error, train test error, and log likelihood. So also something indicated by the reconstruction of the links for the 3 models, we can actually see that ILA, our model, is actually closer to the true representation of the links. You see here that captures more of the noisy links there. Even more interesting is the application of the model in a bigger data set of almost 1,000 genes, human genes in this term, and then in this example. And we found out that ILA found a more meaningful group of genes in the sense that we looked at the groups found by the different models, and we looked at the members of each subcluster in ILA and in our model, and we saw that there it finds genes, assigns genes to clusters that are more closely related in the sense that are involved in the same biological process. And also we are able to plot this assignment to classes and subclusters, but let's keep that. It's just like it gives what I want to point out here is that by allowing a hierarchy in the assignment, we allow for a straightforward visualization of the results. So I want to step back and think, why is this useful? So this is useful because it actually indicates that choosing a model is a very difficult thing. And it depends on whether you care about the predictive performance or about how fast your model wants to do the inference. In nonparametrics, mainly we care about intuitively about the performance of the model. We want to be able to predict correct the model, to capture correctly the data generating mechanism. And that's exactly what I tried to show here by allowing for an infinite number of parameters. I was able to capture better predictive performance and more meaningful group of genes. That's it. Thank you very much. I'm sorry I ran out of time a bit. Happy to take any questions now. So genomics, this is an example of genomics. This is how Bayesian nonparametrics modeling can be used to genomics, applied on genomics. This is something that people have not done extensively in genomics, if I'm not mistaken, Stephen. Thank you very, very much. I think we're good to go now.